All right, so this is part 2 of chapter 5 from the Chem 1212 Clue curriculum. And the first lecture, I went over more temperature and kinetic energy. And this particular lecture is going to focus more on heat, transfer of heat, and its effects on physical and chemical processes. All right, so thermal energy, we just mentioned it briefly in the last lecture, but really didn't talk about it at all. It is a type of kinetic energy, and for a textbook definition, it's energy possessed within an object due to movement of the particles. So just like you jumping up and down to get warm, particles and molecules move. The more they move, the warmer the system or the more thermal energy the system has. And if you remember, thermal energy depends on the mass, okay? So the more mass you have, the more thermal energy you have. Heat is a process, really. It's the transfer of thermal energy from one system to another. And it's done in a number of ways. One of the more common ways is through collisions of molecules. So remember, thermal energy is a type of kinetic energy. And so if you have molecules or particles that are moving faster and faster, they're going to have more collisions. And in those collisions, they're going to transfer some of their kinetic energy to other particles. And that's how heat gets transferred from a hot substance, which has high kinetic energy, to a colder substance, which has lower kinetic energy. It's through the collisions of the particles. All right, heat capacity is a really important term, and it's something, again, that you should be able to have a brief discussion on, be able to explain on a homework question or quiz or task question. All right, heat capacity. Again, first textbook definition, and then I'll kind of talk about it more common language. It's how much energy it takes to raise the temperature of a substance. Okay. Now we're going to talk about what we call specific heat capacity. All right. So that is, again, how much energy it takes to change the temperature of a substance by 1 degrees Celsius. Okay. So I remember learning this still as a student because I was thinking, wait a minute, what if I apply heat to different substances, they're going to change temperature at different rates? Yeah, I guess absolutely. And your common sense knows that even if you haven't thought about that. So I like to explain going to the beach on a hot summer day, and if you're barefoot, you run across the sand and it's like your feet are burning off, and then you're like, whoa, and you go into the water, and then it feels freezing cold. So how is it that the earth, the sand, and the water are at the same temperature? They're both under the same sun, and yet one feels hot and one feels cold. That has to do with the specific heat capacity. It's very different for sand versus water. So again, here's the definition written out. Molar heat capacity, I don't talk about that too much, but sometimes I see it on exams. It's the same concept, but instead of raising 1 gram of a substance, it's to raise 1 mole of a substance. So obviously the value is going to be larger. It's interesting to look at the different specific heat capacities of different substances. So just look at this column for a moment, and you can see the specific heat capacity of water is really high compared to other substances. So what exactly does that mean? Let's think of the definition again. So specific heat capacity is the energy it takes to raise temperature by 1 degree. Okay? So if you have a high specific heat capacity, that means it takes longer to heat it up, right? It takes longer to heat up. So what has a lower heat capacity? Well, these have lower, but what really has low heat capacities are metals. Metals often have heat capacities actually less than 1, which means they heat up very rapidly, and you probably know that intuitively too. So when you walk across the beach and burn your feet off on a hot summer day, and then you jump in the water, it feels freezing cold. It's explained by the specific heat capacity of water, which is really high. So let's kind of test. This is an important concept. And so let's kind of test your understanding. So I would read this question and then turn off the video for just a couple minutes and see what answer you would come up with. All right, so which substance will reach the highest temperature first? I should have said that first, or quickest, if the same amount of heat is added to 10 grams of each. So, another way to approach this is to look at the units. They're important to know for specific heat anyway. Joules is a unit of energy. So the units give you the definition. It's really how much energy does it take, and then look in the denominator, to raise the temperature 1 degree Celsius, and that's 1 gram of material. So it's joules per gram per degree Celsius. So remember, the higher the specific heat capacity, now specific heat capacity is abbreviated with a capital C. So the higher the specific heat capacity, the more resistant to temperature change it is. The higher the specific heat capacity, the more resistant to temperature changes. Okay. And so this one is saying which one will reach the highest temperature. So that's one that's going to heat up real fast. So that's one that has a low specific heat capacity. So silver looks to me like it has the lowest specific heat capacity of the substances on this table. And so it would reach the highest temperature with the same amount of heat. All right, so now we're going to start applying some of our knowledge. We're going to start combining it together. Intermolecular forces, phase change, temperature, and all that. So kind of going to walk you through. Draw the Lewis structure for water. And so if you're feeling confident, turn this off and see if you can do this page by yourself. If not, I'll walk you through. I'm hoping you remember how to draw Lewis structures. If not, then I would recommend, again, going to my YouTube channel and searching for Lewis structure. But if you have water, which is H2O, just very briefly to write a Lewis structure, you want to count up total valence electrons. So that's 6 for oxygen, and hydrogen has 1 valence electron, but there are 2 hydrogens. So that means we have 8 valence electrons that we have to place with our Lewis structure. And, what did I do? Okay. So, do this. Hydrogen can only hold 2 electrons, so we've used 2, 4, 6, 8. All right, so that is a Lewis structure for water. It said to draw them for 2 water molecules so that we can show intermolecular forces. And what are the intermolecular forces, IMF, that are present? Well, let's see. We have hydrogen atoms that are directly bonded to an oxygen, so we know they can hydrogen bond. So we have hydrogen bonding. And then if we have hydrogen bonding, you have all the rest too. Dipole, and London dispersion. All right. So that's liquid molecules. Now, gaseous molecules, what happens? So if this is a liquid, and by the way, we'll go over this more later, but you show intermolecular forces with a dotted line to show that it's not really a chemical bond, just an attraction. But if you were to draw partial charges on the water molecule or dipoles, Because oxygen has a higher electronegativity, it would have a partial negative charge, and the hydrogens would be electron deficient because oxygen's stealing them all. And so, as with all substances, opposite charges attract. And so that's where I'm getting that the oxygen from one water molecule, because of its partial negative charge, is attracted to the hydrogen of another water molecule with its partial positive. So now if you change phases, if you add heat and you make water go to the gaseous state, what's going to happen on a molecular level? Well, they get a lot farther apart, right? You've given the water molecules kinetic energy and enough so to disrupt, break away, loosen the intermolecular forces. So in a gas, the molecules are farther apart, and so they may still experience some attraction, but it's going to be a whole lot weaker, okay? They're going to be farther apart. And as a matter of fact, it's pretty safe to assume that gases have minimal to even zero intermolecular forces because they're so far apart. So let's look at the three different phases of water: solid, liquid, and gas. And let's look at on a molecular level. Let's think about it. So in the solid phase, as always, the molecules are packed tightly. They're a little bit more loosely packed in the liquid phase, and then they're pretty far away in the gas phase. And so the question this asks is, why does it take more energy to raise the temperature of liquid water? Okay, so to go from a liquid to a gas is more energy, okay, than from a solid to liquid, in other words, melting. So melting, it's not just water, that's most substances, if not all of them. Melting takes quite a bit less energy than boiling. And I want you to think and see what you would come up with in trying to explain that. And I don't know if you hear my doggies yet, but they're getting restless. So what it is, if you think about it, if you go from solid to liquid, you're just loosening the intermolecular forces. You're not eradicating them. You're not eliminating them. You're just loosening them enough to let the molecules get farther apart. But when you go from a liquid to a gas, you have to completely get rid of the intermolecular forces, which takes more energy. Okay, so pretty much boiling will always take more energy than melting. Okay, so talking more about phase changes. As we add energy to any sample, and we said before, that means the kinetic energy of the particles increases. And remember, there are different types of kinetic energy. There's the translational, which is just like running from one side of the room to the other. And then there's vibration and rotation. And until a substance reaches the temperature of a phase change, its temperature will increase steadily, just like you would expect. And interesting enough is once a phase change has begun, all of the energy added is used to overcome the intermolecular forces. Therefore, during a phase change, temperature remains constant. So if you were boiling a cup of water and you put a thermometer in it, it would gradually increase, and then when it reached the boiling point of water, which is 100 degrees Celsius, it would stay at that exact temperature, 100 degrees Celsius, until all of it boiled off. I've always thought that's kind of interesting. And it's not that the energy isn't being used for something, it is. It's being used to loosen up intermolecular forces to allow for the phase change. We alluded to this a little bit earlier, but just to kind of make sure it's sunk in. So we've talked about heat, why things heat up at different rates. And heat transfers, we mentioned earlier, that always goes from the higher temperature object to a lower temperature object. But how exactly does heat transfer, right? Heat energy is a form of kinetic energy, it's movement. And so how does it happen? It's through collisions, okay? So if you have a hot object, that means the molecules of the particles have higher kinetic energy, and so they're moving around rapidly, and they are going to collide more often. So when they collide, particularly with a molecule with lower kinetic energy, they're going to transfer some of that energy. And so the molecule that picks up the extra kinetic energy is going to increase in temperature, and the ones that gave it away are going to decrease. And so that's how you get a hot object to transfer its heat to a cooler one. So we have talked about specific heat capacity in a theoretical way. But as I told you, we're going to have a lot of graphs in this class. So what if we graph temperature versus thermal energy, okay? And one of these substances is water, and one of them is ethanol, which I wouldn't expect you to know the formula, but this is it, CH3CH2OH. And which substance is more sensitive to temperature changes? So this is just an interpreting the graph question. So again, which of these substances, okay, which of these lines representing a substance shows more sensitivity to temperature changes? Okay, so basically we're saying which one has a larger change in temperature, so that's the y-axis, for a smaller change in added energy. And it's the one with the highest slope. Okay, so you can think of kind of delta y over delta x. And the one with the larger change in temperature would be this line. Okay, so which one corresponds to water? Well, let's see. Water has a specific heat capacity of 4.18. Ethanol has a specific heat capacity of 2.44. So turn off the video for a minute. Go back a couple slides if you need to. And tell me which of these lines corresponds to water. I'm going to tell you right here, this is water, the bottom line, the one with the shallower slope, and ethanol is the top line. So let me walk you through why that is. The most important thing to learn here is what a high value or a low value of specific heat means. Water has a very high specific heat. What does that mean? It means it takes a lot of energy, a lot of joules, to raise the temperature. Okay, so it takes a whole lot of energy. You got to add a lot of energy to get just even a little bit of temperature increase. Okay, whereas ethanol, which has a lower specific heat capacity, takes just a little bit of energy to raise the temperature a lot. This diagram is called a heating curve, sorry. Okay, and you can see that temperature is along the y-axis and heat added, or sometimes they just call it time, is along the x-axis. And all heating curves have the same general shape. So you have these diagonal areas, and then you also have the plateaus or the flat areas. Okay, so you should be able to interpret a heating curve, but you should also be able to sketch one. And so let's look at it for a minute. This happens to be water. And so let's say that we start, when do we know that water's a solid ice? So we'll just say minus 10 degrees C, all right? We know it's a solid at that point. But then at what point do we know that ice begins to melt? Okay, melting and freezing point are the same thing, by the way. So that would be 0 degrees Celsius, okay? So I don't know if you remember me saying, but if you didn't get it down now, that during a phase change, temperature remains constant, okay? Temperature is constant during any phase change. All right. All right, so then once all of it melts, we begin increasing the temperature again as we're adding heat, okay? And that is the liquid phase. And then at some point it is going to boil, and we know for water the boiling point is 100 degrees C. And so the temperature is going to stay constant again at 100 degrees C until it's all boiled off. And then steam can start heating up again, getting a higher temperature. And by the way, that's why boiling water isn't as dangerous as steam, because boiling water cannot get hotter than 100 degrees. Steam can get as hot as you want it to. All right, so this is the basic structure of a heating curve. And so again, the plateaus are where the phase changes occur, and then the sloped areas are when temperature is increasing. We are going to start doing some calculations with heat transfer and physical and chemical processes. So in order to do so, it's important to know what direction heat is flowing. And so chemists classify the system we are studying. So that might be the chemical reaction molecules itself, for example. So the system is, again, what we're studying. The surroundings is literally everything else. So let's say that you have a chemical reaction occurring in a flask. Okay? And let's just say the chemical reaction is occurring in water. So the system would literally be the particles that make up the chemical reaction, and the surroundings would be everything else. So the water and the container, okay, and the air are all surroundings. I'm sure you've heard of exothermic and endothermic, and they are each represented by a different mathematical sign. So this is your system in here, okay? If your system is releasing or giving off energy, that is, we call that exothermic. But it's important to also know that we use a negative sign in any type of calculation for an exothermic process. And that's because if a system's giving off energy, what's happening to the energy of the system itself? The energy of the system itself is going down. It's getting more stable. So since the energy is going down, we use a negative sign, okay? Now, if the system itself is accepting more energy from the surroundings, that is an endothermic process. And in any type of calculation, we give that a mathematical sign of positive because the energy of the system is increasing. Now, for our purposes, the heat of a system we're going to call enthalpy, okay? So at constant pressure, which is what we're going to talk about, just atmospheric pressure. So at constant pressure, again, which is what we're doing, enthalpy equals heat, one and the same, okay? And enthalpy, or heat in our case, is abbreviated with a capital H. So again, if your system is taking in heat from the surroundings, that is an endothermic process, and enthalpy, or heat of the system, has a positive sign, which simply means it's greater than 0. All right, on the other hand, if the system is giving off heat, like combustion, okay, that means that it is an exothermic process, and we give that a negative sign to the system. And that simply means that the change in enthalpy or heat for the system is less than zero. Okay, change in enthalpy or heat is going down for the system. Now you got to be really careful of this because whether you're talking from the system perspective or the surroundings perspective, it's going to be opposite. So you've got to be really, really attentive there. Now, because there's conservation of energy, if the system is taking in heat, what's going to happen to the surroundings? It's got to be getting its heat from the surroundings, right? So the surroundings will get cooler. On the other hand, exothermic, if the system is giving off heat, like a combustion reaction, the surroundings are going to get warmer. Now, the system itself, you probably can't measure it, but the system itself has to be getting cooler. Okay, but if you have a fire, pieces of wood are cooling down, but everything outside of that fire is warming up. Now, this is just a simple definition, but it might show up like as a multiple choice or something. So, enthalpy, okay, H, heat, is a state function. There are several functions that are state functions and some that are not. But a state function is something that depends only on the initial and final values. It doesn't depend on the path or the route taken to get from one place to the other. So enthalpy is a state function, which means that we can calculate the change in enthalpy for a process by simply having the enthalpy the difference in the enthalpy between the initial and final states. Okay, so any state function, if you want to find the change in that state function, you can just subtract the values of the initial final, and the middle values don't matter. So, yeah, I kind of like this example. Okay, so let's say you're at the bottom of a mountain and you hike to the top to get to some top of the mountain campsite. If you go pretty much straight up the mountain, okay, or if you go a zigzag path all over the place, what's not going to depend on the path taken? Well, the altitude itself, the 4,800 feet, it's going to remain 48 feet regardless of the path you take, right? So to find altitude, you would just do, height of the top minus height of the bottom, right? And it wouldn't matter what route you took. Can you think of a function that would matter what route or pathway you took to the top of the mountain? I can. How about energy expended, total energy expended by the person doing the hiking? That's going to matter a lot on the pathway. So anyway, that kind of gives you an idea of state function versus not state function. Here's a quick summary of state functions. Again, just simple definition that might be a multiple choice question. This is a nice little thing. State functions are typically represented by uppercase letters, and we'll have a lot of these just in this chapter. Enthalpy is entropy, free energy, pressure, volume, energy, and temperature. Alrighty. Now, things that are not state functions that depend on the path you take, they're typically represented by lowercase letters. So this is heat. Q is heat. W is work. Now, just to remind you, there are two basic types of energy. We've talked a lot about kinetic energy, the energy of motion, but remember there is potential energy too. And that's pretty much energy that's stored within a system. To chemists, probably the biggest source of potential energy is in a chemical bond. Now, the type of energy can change within a system. So there is conservation energy. So if you have a system that has the same amount of energy, but the temperature has changed, then what's happened? That means some of it's been converted to potential energy. Alrighty, onward march towards our chemical reactions and the energy changes that accompany them. The first law of thermodynamics, that's an easy one, is that energy is conserved. Okay, overall energy is conserved. Energy cannot be created or destroyed, but it can simply be transferred or it can be transformed to a different type of energy. So get familiar with these symbols. Q is a thermal energy, or we just call it heat. And little w is the work. Okay, and the units we're going to be using for all of these are joules. Now, work done, okay, work done for our purposes, we're only going to see that for gases, okay? And that's because gases can expand and contract, like other phases cannot. And by expanding and contracting can do work on its surroundings, okay? So, but if there's not a gas, we're really not going to see work done. So if we're not talking about a gas, then the overall change in the system can be represented simply with heat, thermal. So the sign convention, the plus minus signs, are probably the trickiest part of thermal chemistry to keep track of. Almost always we're talking from the perspective of the system. So pretend like you're the system, and that's what's going to determine if it's exo or endothermic. So again, anytime you're adding heat into the system, then Q, or heat, has a positive sign and it's endothermic, okay? If heat is leaving the system, that is an exothermic process, and we say that heat, Q, is decreasing or has a minus sign. Now, listen carefully to this for the next couple minutes because this can throw you off. It's not hard, but it can throw you off. Okay. So if work is done on the system, so let's say the system is a gas, okay? So it can compress and expand. So if we have something from the outside that is squeezing or doing work on our system, okay, that is and I don't really want to say endothermic because it's not thermal. It's a different type of energy. It's work. So I'm going to say endothermic. But the bottom line is the system is taking in some type of energy. Okay. So the sign associated with that, whoops, I'm on the wrong side. Here we go. Work done by surroundings on the system. So the work has a positive sign and it's endothermic. Okay, and the system itself is going to contract. It's going to shrink. All right, so let's go the other way for a minute. If work is done by the system on the surroundings, so if for whatever reason this gas that makes up your system is expanding, maybe we're heating it or something, it's expanding and it's pushing the surroundings away. And so that means that work is being done by the system on the surroundings. It's an exergonic, giving off energy process. So we say that the work is negative there. So I want to encourage you to turn off the video and see if you can answer your question itself. There's no calculation, it's just conceptual. And so go back to the last couple of slides where we're talking about sign conventions and see if you can determine whether this process would be endothermic with a positive sign, which means the energy of the system is increasing, or would it be exothermic? In other words, would the system be releasing energy and therefore be decreasing in energy itself? Alrighty. So let's look at this carefully. Water is changing from -10 to 110. So here we have water. Here's my Erlenmeyer flask. okay? And it's going from a minus 10 degrees, which is really cold, right? And it's being heated up to 110, okay? So has our system, which is the water, has it taken in energy or has it released energy, okay? It has taken in energy, which means it has more thermal energy, okay? So if it's taken in energy, it's endothermic, and so it is associated with a positive sign. Now, as I said before, the little letters Q and W, heat and work, are path functions, okay? So the heat of the system, the heat energy of the system, or the work of the system depends on the path taken. Now, the total energy change is a state function, which means you just need the initial and final values. And again, as a reminder, enthalpy, capital H, is a state function. So again, all you need is the initial and final values. So as I said before, but it's very important to understand, delta H is change in enthalpy, okay? But if you have constant pressure, which all of our examples will, that just means atmospheric pressure. We're not putting anything under a vacuum or excess pressure. And in that case, change in enthalpy and Q, heat, are identical to each other. So that's great. That simplifies our life. Again, if enthalpy change is positive, that's endothermic. And if it's negative, that's exothermic. So we could write an equation, right, that the change in enthalpy for some type of process equals enthalpy final, what it ended up being, minus enthalpy initial. Okay. Pretty much all these change in something values are final minus initial, just kind of give you a heads up. So if the final is greater than the initial, you're going to end up with a positive value, and that means, for delta H, that means endothermic. If the final is less than the initial, you're going to end up with a negative value for delta H, and that means it's an exothermic process. Take a minute and classify these. Now, I'm going to insist in this case that you turn off the video, you take a minute and classify each of these processes as to whether they're exothermic or endothermic, and there's not enough information. Well, the first thing you need to be able to do is decide what the system is. And again, when you're classifying something as exothermic and endothermic, it is from the point of view of the system. So wood burning, okay? So the wood burning is your system, okay? And that wood burning, that's a combustion reaction, is giving off heat. So that is an exothermic process, which means it would have a negative mathematical value if we were to do a calculation. So these are weird. Freezing's weird. I can't wrap my head around it. So this is what I do for phase changes that are weird. That would be condensing or freezing. It's very intuitive to most people that if you're melting or boiling, that the system has to take in heat. It is an endothermic process, right? The positive sign. So the opposite of melting and boiling, going in the opposite direction, and what would that be? That would be, the opposite would be freezing and condensing, right? So the opposite, anything driven in the opposite direction has an opposite sign. So if melting and boiling are endo, freezing and condensing are exo, and they would have a negative mathematical sign. All right, so water freezing is exothermic. Sweat evaporating, okay? So you're doing it from the perspective of the little sweat molecules, water molecules on your skin, okay? And so they are basically, the sweat is boiling, okay? The water's boiling, And so in order to boil anything, you have to take in heat. So that is an endothermic process. Okay. Chemical hand warmer. There's literally a process going on inside that little hand warmer, and that process is releasing heat. So that is exothermic. So just to summarize what I said is the enthalpy change of any process, when you reverse the process, go in the reverse direction, there is an opposite sign that you assign to enthalpy. Let's see how you do trying to take some information given throughout Chapter 5 so far and see if you can kind of pull it together to answer this question. Which of these four substances would have a higher change in enthalpy of vaporization or heat of vaporization? What is that saying? So let me reinterpret that. Which of these substances would require more heat or more energy, right? More heat to boil or vaporize? So make sure that makes sense to you, okay? So if something says what has a higher heat or enthalpy of vaporization, it's saying which would require more heat to boil it off or vaporize it. So look at these structures and turn off the video. IDK is just, I don't know, you know that. I don't know why I'm telling you that. And see whether you think this, it's called methanol or ethane, would require more heat to vaporize. Well, to kind of prepare you, now remember, it's not enough to just say A or B. You would have to explain it in this class too. So again, a reminder that with a clue curriculum, we're going to be asking you why and to explain almost everything we learn, okay? All right, so what happens on a molecular level when something vaporizes? Okay, so here's the liquid substance, the particles of it, right? And when you add enough heat, it's going to go from the liquid phase to the gas phase, so the particles are going to be a whole lot farther apart. So what did you have to do to get it, besides add heat, from the liquid to gas? You had to add enough thermal energy to completely break up the intermolecular forces. So the substance that has the stronger intermolecular force is going to require more energy to vaporize. So you want to identify which of these two has the strongest attraction to itself, strongest intermolecular force. I mean, like if you had several molecules of each, which would be more attracted to each other? The one that's more polar, right? The one that has stronger intermolecular forces. And clearly CH3OH is going to have hydrogen bonding, which is a whole lot stronger than this hydrocarbon, which only has London dispersion. We've talked a lot about thermal energy, exothermic, endothermic, etc. How do we actually measure that in a lab? We use a process called a calorimeter. Okay, and it's basically a highly insulated vessel in which you can have your process going on. There's typically a thermometer in it, obviously, and a stir to keep the heat uniform. So here's a formula that you'll want to jot down someplace handy to get to and also memorize it. But it tells us that the thermal energy is equal to the mass times the specific heat capacity times the change in temperature measured. So using that calorimeter, we can put a substance in, and as long as we know its mass and the specific heat capacity, and then we measure the temperature change, we can calculate how much heat was generated by that process, or generated or taken in. So just to kind of keep units straight too, any type of energy that we deal with, we're going to use units of joules. Mass is grams. Okay. the units for specific heat capacity are weird. It's joules over grams times degrees Celsius. And then change in temperature, make sure that the temperature readings are in Celsius, or Kelvin would work too. All right, so let's do a couple of examples of these. Here is a typical calorimetry problem. So in this problem is asking for the specific heat of an unknown metal. So specific heat is capital C of some metal. That's what we're looking for. They give us the mass. How nice. Okay. And they give us a temperature here. They're using a calorimeter. Here's another mass. It's water. And here's another temperature. So this can get quite complicated, but hopefully from the information given, you know that we're going to use I call this the QMCAT equation, where heat equals mass times specific heat capacity times change in temperature. So I'm going to spend just a couple minutes setting up how to actually work this. Let's just say, okay, we're trying to get information about the metal, so let me fill in what information I know about the metal. I don't know Q for the metal, right? I know the mass of the metal. All right, so we'll fill that in, 50 grams. I don't know the specific heat capacity of the metal. And change in temperature. Remember I said these changes are typically final value minus initial value. Now the final temperature for the metal is not specifically laid out for you in the problem. However, it's very important to realize that final temperature when two objects of different temperature are in contact with each other are the same, okay? So the higher temperature substance, in this case the metal, is going to transfer heat to the lower temperature substance, the water, until they're both at the same temperature. So the problem did tell us the final temperature of the water, and that is the same for both substances. So the metal final temperature minus the initial temperature of the water, obviously your delta T then is going to be negative here. So since all of the information we need to solve for the specific heat capacity of the metal, which is what the problem is asking us, is not given, that's the kind of situation when you need to set up, you need to use MCAT equation for both substances. So in other words, the heat that is lost or gained by the metal is equal in magnitude, but minus in sign. One of them's gaining heat, one of them's losing heat, to the heat gained or lost by the other substance, in this case, water. And so using the MCAT, same thing. Okay. Make sure you put this minus sign in. This is the most common student mistake, is leaving that out. Right. Okay, so I'm going to go ahead and plug these values in. It's worked out in the next page, but I would like to see you work through the math on your own. It's not high-level math, but it's so easy to make a mistake. So I just want you to kind of make yourself go through it, and then make sure you work the practice worksheets also. All right, so the final temperature of the metal was 25. Its initial temperature was 100. Make sure you remember the negative sign. Specific heat capacity of water was given. And let's see, final temperature of water, same as that for metal, 27.5. Initial temperature of water was 20. All right, so again, I would suggest turning the video off for a minute, working through this math, what you're trying to solve for a specific heat of metal. And then you can go to the next page and it has it worked out for you. Here we go. Remember conservation of energy. So whatever energy is given up or taken in by the system, because of conservation of energy will be taken in or given up by the surroundings, okay? So because of that, you can set the Q, or the heat of, in this case, the water, which is the surroundings. It's going to be equal in magnitude but opposite in charge of the heat of the metal. So basically, you're going to be doing Q equals MCAT, right? You're going to be doing mass of water times specific heat capacity of water times change in temperature for water. And you're going to set that equal to minus, and then the same things for the metal. The mass of the metal, specific heat capacity of the metal, and change in temperature for the metal. Okay. And you can see Q drops out of the equation then. You just have MCAT of the water equals minus MCAT of the metal. All right, so plugging in the values for water, we had 50 grams. The specific heat capacity of water is very well known, 4.184. And the temperature change experienced by water is 7.5 degrees. I think the final temperature of the water, the hottest it got was 27.5. And the initial temperature was 20 degrees C, okay? So the change in temp was 7.5. Plugging in what we know for the metal. Now, I'll point out this right now. This minus sign is left out probably half the time by students. It's just oversight. So be really careful to, and it doesn't matter what side minus is on. It just means one side's opposite of the other. I would put a minus sign and then put brackets around all of the variables so you carry your minus sign correctly or distribute it correctly. All right, so plugging in what we know for the metal and then rearranging the equation to solve for specific heat of the metal. I'm not going to do this here. I will do it in class, but you need to make sure that you can take this equation and simplify it mathematically so that you solve for the specific heat of metal and do in fact get 0.43. Okay, another really useful application of the QMCAT equation is to actually do some quantifying on a, remember this was called a heating curve? When you take a substance and you heat it up and then you observe, you get plateaus where the melting and boiling points are. This is obviously water again because we know the melting and boiling point. But you can quantitate the exact amount of heat that's required at each phase. And so I'm going to walk you through how to do that. But first, I want to point out that look at the equation for QMCAT, okay? It has a change in temperature. In order to work, you actually have to have a change in temperature. So remember the plateaus, when it's changing phases, melting or boiling, there's no change in temperature. It stays at the melting or boiling point. So you cannot use QMCAT. You can't use that for a phase change because there's no temperature change, okay? So you have to use a different equation during a phase change, and it's a really simple one, and it's, I don't know why these Q's are capital, but it's basically Q equals the mass of the substance times what we call heat of vaporization. It's a standard value like in a reference book, heat of vaporization for water, or enthalpy of vaporization. Now, weird is that fusion means melting. I don't know why they don't just say melting. So in a similar vein, the melting point, the heat involved to melt something completely off, equals the mass of the substance times what we call heat of fusion or enthalpy of fusion. And so you can calculate the individual heat required for each of these 5 processes, or if you're asked to calculate an overall heat for the entire process, then you would just ultimately add them all together. So we will work out a problem on a heating curve in a bit, in a few slides, and you will also be asked to work one out in your homework and probably on your first test. So this is something you should spend some time practicing. Remember, I practice worksheets posted in D2L in the Chapter 5 tab, so you want to start working on those. So how much heat does it take to melt an ice cube? So you'll always be given a beginning temperature, so it might be minus 10 degrees. We know that's ice, right? And then you may be asked to calculate the total heat it takes to get to steam at maybe 150 degrees Celsius, okay? You'd have to use a heating curve and do 5 separate calculations. One quick note about calculating the heat for a phase change, melting or boiling. I did mention that when doing so, it was mass of the substance times heat or enthalpy of fusion or heat of enthalpy of vaporization. However, just to kind of give you a heads up, sometimes the heat or enthalpy of fusion and vaporization, instead of being given in units that are joules per gram, like that's energy per gram of substance required, every now and then the heat or enthalpy of a phase change is given instead in units of joules per mole. So how much energy is required per mole of the substance, not gram. So I typically won't do that to you in a test, but on your final exam, which I'm not going to write up, it may be that way. So as always, pay very close attention to the units. And if you're doing this type of calculation and the units are joules per mole, then your quantity better be mole, not mass, right? So that units cancel. So if the units in the delta H value are joules per gram, then of course you're going to multiply by mass, which has units of grams, like I originally said. Just make sure that all the units match so they cancel. All right, so here's a sample problem. The wording on these problems can be really tricky, so listen very carefully. You probably won't have time on a test to do 5-step calculation, taking ice from negative 10 degrees to 150 or something. So on a test, you'll typically, the wording in the question will maybe have you do 1 or 2 calculations, not 5. So this particular sample, what is the heat required to melt 25 grams of ice? Well, a lot of students would read that and go, I have no idea what to do. I mean, you didn't give me any numbers other than 25 grams. Well, what is the equation that we need? We are melting, okay? You know what temperature, you know what the melting point of water is, right? It is 0 degrees. Remember that melting point equals freezing point. They're just approaching it from different directions, and they're both 0 degrees for water. And the boiling point equals the condensing point for water too, and that's 100 degrees. All right. So we're talking about melting, and any phase change, you cannot use MCAT because there's no change in temperature. So here's what we're using. And remember that F stands for fusion, which is the same as melting. This is the equation we're using. You were given the heat of fusion of water. Pay attention to the units. It's joules per gram, so we will multiply by mass. So all we do now is give the mass given to us, 25 grams, and we multiply it by the delta H of fusion, 334 joules per gram. Grams cancel, just multiply them together, and you get that the heat required to melt that much of water is 8,350 joules. Here's kind of an overview on your homework. If I were you, I would practice doing a problem that goes from through all 5 steps of the calculations just to get good practice. But just as kind of reminder, this diagram labels each section as a different letter, and you have to do each calculation completely separate for each section of the graph, and then at the end add them all together. So here, okay, going from minus 40 to 0 degrees, that's basically warming up ice. Okay, that's point A. You would use the MCAT formula. All right, and what would the change in temperature be? Well, if we look at the graph, it goes to minus 40 to 0. So the change in temperature, its final minus initial, would be 40 degrees. Heat capacity, specific heat capacity. Now notice that the specific heat capacity for different phases of the same substance is different. So look at solid, liquid, and gas for water have different specific heat capacity. So be careful. All right, so, and then you would go to melting the ice. And that's when you would use this equation and pay attention to units, joules per gram. So you'd multiply this by the number, however many grams you have of the substance. All right, so, and then now, region C, you're just heating up the liquid again. So you can use MCAT, temperature's changing. And the change in temperature at this point, it'd be 100 degrees minus 0 degrees. So delta T of 100. Okay, so I think you get the big idea. I cannot emphasize enough that you need to go to the practice worksheets I've posted in D2L under the Chapter 5 tab in content and work a bunch of these, okay? That is it for this lecture.